So hello everyone. I would like to welcome you to my presentation entitled with IoT, AI and DLT for climate smart agriculture. So I'm Stephan Adam. First of all, I have to say that I do have my background more in climate modeling, so I'm actually not a blockchain expert. However, I will do my best to present the things we're working on at ETO GROUP in these directions. So mainly my talk will focus about, let's say, the upcoming agricultural portfolio for precision agriculture that ETO GROUP is working on at the moment. To start with, I would like to give you an outline. So first of all, I would introduce you to the term climate smart agriculture and put some emphasis on irrigation because we have a lot of products that actually work for that deal with irrigation. This will be followed by a summary of the agricultural portfolio of the ETO GROUP. And I would like to say a few more words about an interesting topic we're working on, which is where we already apply machine learning, which is plant electrophysiology. That will be followed by our DLT applications, so why, how, and where do we apply them. And finally, I would give you an overview basically of our ideas about sensor data fusion and artificial intelligence, and how artificial intelligence could actually help with giving basically recommendations to farmers based on the sensor data we're measuring. And finally, I would like to summarize basically or as a conclusion, summarize the effects our products could eventually have on influencing climate change mitigation. So what is climate smart agriculture actually about? There's an official definition by the Food and Agriculture Organization by the United Nations. And climate smart agriculture actually aims to provide a sustainable increase in agricultural productivity and income. Furthermore, another goal is to adapt and strengthen the resilience, so basically strengthen climate change mitigation. And furthermore, it's also about the reduction of greenhouse gas emissions like nitrous oxide, methane, or also CO2 from agricultural fields, and also the removal of greenhouse gases like through carbon sequestration. A very important topic for climate smart agriculture is irrigation. So irrigation became much more important in the past years, as we can also see here on that slide, which I took from a recent publication about the role of irrigation in the Earth system. So just to give you a few numbers, so irrigation actually accounts for 70% of the global freshwater withdrawals, and 20% of the global food cropland is irrigated. And according to the United Nations, 30% of the world food is actually produced by irrigated fields. And furthermore, 45% of the irrigated water is coming from groundwater. So that's from actually water that's remained in the ground or in the soil for several thousand years in some cases. There's a growing demand for irrigated land because of stronger droughts, and furthermore, irrigation already altered a level where it actually changes the global water cycle and other biogeochemical cycles, for example, the nitrogen cycle. So in their publication, McDermott et al. Worked out a couple of regions where irrigation is really important globally. So that's particularly South Asia, Northern China, the United States, Europe, and Egypt and Sudan. And to further emphasize the role of irrigation, I prepared a slide about the current state of global state of water scarcity. So 1/3 of the global population are affected by drought, at least per month per year. And globally, and global freshwater availability has exceeded its planetary boundaries since a long time. In that publication, Lainze et al. Basically identified several regions that are most affected by climate change-induced drought. And interestingly, most of these regions actually showed up in the previous slide I showed you. So that basically underlines how important irrigation is for water scarcity and drought resilience. Yeah, to give my presentation a bit of a frame, I would like to answer two questions in the end. The first one is whether we really help to mitigate climate change with the products that we will offer. And the second one, I think, which is even similar important, is if we really help the people most affected by climate change-induced drought. So with that, I would like to come to the agricultural portfolio that we will enter the market pretty soon. So a few people already have been to our booth In the other building, there you can see the FarmSense. Basically, that's an IoT feasible weather station that is self-sufficient, has a self-sufficient power supply via photovoltaic cell. And it's possible to transmit the data via LoRaWAN and NB-IoT. So two different protocols are available. It measures the full suite of meteorological variables, so namely temperature, air humidity, pressure, wind speed, direction, solar radiation or global radiation, also precipitation. Connectable to these sensors are soil moisture and soil metric potential sensors. So here you can see a soil moisture sensor. Down here, that's a metric potential sensor. Soil moisture basically tells you how much volume of water is actually in the soil, while the soil metric potential or water potential sensors tells you how hard it is actually for the plant to access the water. So in combination with that, with these products, we also offer IoT-ready irrigation wells. They're connectable via NB-IoT and Bluetooth Low Energy. LoRaWAN is actually planned. An interesting topic for this product is that it is programmable via cell phone apps, so the user basically can schedule irrigation times, and in the future it is actually planned to do something like a closed-loop automatic irrigation system in combination with the sensors I showed on the previous slide. We also offer our own LoRaWAN gateway, so whoever is not familiar with LoRaWAN, so that's a local area, low power radio transmission protocol that needs a gateway to basically enter or to write these values into a cloud, for example, or a server. That's an interesting part about this gateway is that it has an extra long antenna to allow long range distance. Data transmission, what is a very important topic in rural areas where you often don't have good coverage with these networks. The next product I would like to introduce is the Farm Lab. That's actually a small device that allows to measure or estimate soil quality and soil health by giving the activity or measuring the activity of extracellular enzymes in soil probes. So we have 5 different enzymes. Most of them are related to the carbon cycle in the soil, but also to the nitrogen and to the phosphate cycle. So that makes this, for example, an interesting product also for carbon sequestration in soils. We also offer our semi-automated spraying systems. They were originally developed by Innovel, a company that joined ETO GROUP and now turned into Farm United. Farm United is also the brand under which we will sell all of these products I'm presenting here at the moment. Now I would like to come to the plant electrophysiology part. So together with Vivent, it's a partner company for these projects from Switzerland. We are developing small devices that allows to measure electrical signals in plants. And plants do actually use these electrical signals to communicate within their tissue. So as soon as a plant, for example, is infected by a pest or whether it has any kind of a nutrient deficiency, you can, by measuring these signals, you can determine that. And that also involves machine learning. So basically these high frequency voltage time series that are measured here are analyzed by several machine learning algorithms, deep learning, Gaussian process learning, and from that we would like to give the farmers recommendations whether basically their plants are in any kind of harmful states or if they're doing well. To further show basically the possibilities of these signals, I would like to summarize a publication by Daniel Tran et al. From Agroscope, who did experiments with the plant physiology sensor on tomato plants under greenhouse conditions. They had two different groups of plants. So one had sufficient nutrition, while the other plant group had was exposed to an artificial iron deficiency. And they used supervised machine learning algorithms to detect basically this iron deficiency from the voltage time series they were measuring. And the really interesting result was that the first visible symptoms, so these plants, they often show malnutrition by recoloring of the leaves basically, were only visible after only 8 days. And with the trained model, they were able to detect basically the malnutrition after 2 days. So that's getting close to real time and will be a really interesting topic for agriculture to introduce. So together with Vivent, we are working on an IoT-ready version of that device for auto agriculture. It's also collectible via LoRaWAN. As I already said, we're analyzing voltage time series, and we're quite confident that we can detect several nutrient stresses and also can differentiate between them, and also can detect the infestation by various pests and fungal diseases. And furthermore, we can recognize water stress and heat stress. And the really important topic is that all of that is in real time or close to real time, what is not possible with the traditional methods that are used so far. As we use machine learning algorithms, we only will achieve a certain degree of confidence, so roughly 80%, but that can be further enhanced by having plant-specific algorithms. So basically, as the device is located on the plant, so the models need, let's say, some amount of retraining, and then they fit basically to the local conditions. And another very interesting topic is that new stresses can be actually induced with that sensor without any hardware changes. So it's simply basically the algorithm that does the quantification in the end. So to set the floor for the upcoming DLT slides, I would like to give you an overview about the Farm United ecosystem we are working on. So we do not want to only basically sell hardware and measuring sensor devices. We basically want to cover the full cycle of the data. So that does not only include the measurements, but also the analysis and visualization of the data. And furthermore, also, basically recommendations for actions, so irrigation and plant protection. And the final aim is basically to optimize and reduce the water usage on agricultural fields, and also the use of plant protections, or also nutritions basically for plants. So that brings me to the DLT applications. So the basic idea why we are applying distributed ledger technology is that we want to give the users or the farmers that buy our products back the sovereignty over the data. So to frame it a bit, the data should actually belong to the farmer. And it's stored decentral and secure thanks to DLT. And all data can be managed via a cell phone app. And furthermore, basically, as it is quite tough basically to get a huge amount of data into blockchain or distributed ledger tangles, we will supplement that by a cloud-based backend. We chose IOTA for that. This had mainly two reasons, because IOTA offers an efficient solution for data exchange. And furthermore, it's a much more energy saving compared to other blockchain approaches. In detail, basically, the data handling works as follows. So we have our sensors that have a hardware security chip implemented, and with that, basically, the sensors encrypt their data, send them basically through a wireless protocol to a payload processor, and from there, the sensor registers itself with a so-called zero-value transaction, so it registers its hash value within the IOTA tangle, and then sends frequent data packages basically to our cloud backend. And hash values of these data packages are then stored regularly in the IOTA tangle. And with that, basically, the integrity of the data is secured, and also temporal reliability is given. And as the IOTA tangle only stores basically a recent, I wouldn't call it a snapshot, but not all the data that was given into the tangle, we also will operate our own permanode basically to make all of the data accessible to the users. As IOTA also offers coins basically that allows to sell data, we are also working on our DLT-based marketplace. Here IOTA could show its strength by its fast transactions, and with that we would also give the farmers basically the possibility to have an additional income by selling the data to other people. Here blockchain technologies are very interesting at that point, as they allow micropayments. So in theory, it's basically possible to pay or to sell a single data point, for instance. And furthermore, we want to make use of something like a network effect. So basically, farmers should allow farmers basically to give recommendations among them others. So, for example, one farmer behaved in a similar situation in that way, and we could basically give these recommendations also to other farmers. With that, I would like to come to the sensor data fusion part of my presentation. So the background why we're working on this is actually that I've presented you a whole bunch of different sensors, and you have to think about the agricultural field basically as a system with different interactions. And all of these different sensors, they measure or estimate basically a state parameter of the system, of different parts of the system. So to give basically the farmer a comprehensive overview of what is actually going on his fields, there is the need basically to fuse all of these different data sets. So for example, the enzyme reader I presented you gives you an overview about the nutrition budget in the soil. The plant physiology sensor tells you something about the state of the vegetation, while the water potential and the soil moisture sensors tell you how much water is in the soil and how it's accessible. And basically the farm sense tells you something about the local weather situation. And to bring all of these information together, I would like to use a process-based model as basis for the data fusion, so that basically numerically solves all of the governing equations for the water and heat and nutrient budgets, for example. Such a model would also allow to do forecasts into the future, so you basically could help people to schedule irrigation times, for example. However, such models are often pretty parameter sensitive, and these parameters are often locally not known. And therefore, basically, I would like to calibrate these model parameters with the help of the local measurements that we're doing. And one of the possibilities to do so is the Ensemble-Kalman filter. So that's a Monte Carlo-based approach of the famous filter originally developed by Kalman. And during such a calibration approach, basically you start with an ensemble of differently parameterized model states, and you propagate them in time, basically inflate the model states, and then you do an update with that equation. So on top here with newly available measurements or observational data, basically shrink the ensemble back to the I wouldn't call it true value, but to the estimated true value. And with that, basically you do inverse parameter learning. So this actually means that you are not inverse actually means that you are not learning the parameters directly, but you basically deduce them from the measurements you are doing. However, such approaches to make them computationally feasible, they often come up with some assumptions which are violated. For example, you assume Gaussian error distributed measurement and observation errors, and you also, for example, here on top you can see that the update is done by a linear equation or the weighted observations. And this is, and basically for all of these complex models I'm talking about, this is often not the case, so these assumptions are violated. So that's one of the places where artificial intelligence or machine learning could come into play. So because first of all, I have to say basically that these algorithms I showed on the previous slide, they are basically, they solve the very basic same equation on a very basic level as artificial intelligence. So that's basically an Bayesian function, and it's optimized. However, data assimilation assumes linearity, and artificial intelligence or machine learning is pretty efficient in producing nonlinear processes. And these models I was talking about, they are often mutually coupled, the equations in there, and so they are nonlinear and they do not show Gaussian errors. So a combined approach between basically a process-based model and an artificial intelligence or machine learning-based update or parameter-learned framework shows pretty promising results, as was recently shown in a publication in Water Resources and Research by Zhang et al., for example. Another thing where artificial intelligence can come into play is basically that you also can replace certain processes in these process-based models by learned models, by machine learning models. And here a nice example that I found is by a publication by Zaha et al., where nitrous oxides emissions from agricultural fields were calculated. And so there are process-based models, traditional models existing in that field in there, but they only basically work in a very pure level with only 20% accuracy. However, with a coupled artificial intelligence and process-based models, they were able to get much better results than what has been there before. So one might actually ask, why if artificial intelligence or machine learning works in such a good manner, why not simply using a pure artificial intelligence approach? Well, I would say there are two reasons why I'm a bit suspicious with doing so. First of all, the first one is actually, I would say, a rather basic thing that I would say that pure artificial intelligence-based model or machine learning models are often pretty hard to extend. So as soon as you want to include an additional process that was not there in the original training data, yeah, that's basically you have to retrain your whole model. The other thing is that yeah, most of the machine learning approaches, they actually rely on, yeah, basically similar situations that have been there in past situations. So if you use a time series of historical data, then you train your model to do forecasts. And so for statistical physics or, yeah, basically ergodic theory, you can show theoretically that it's impossible or virtually impossible to find a good analog state for systems that do have a dimension larger than 6 to 7. And to give these numbers or a bit of a frame, a usual weather forecast basically is assumed to have a dimension about 1,000 to 10,000. And even with these more simple agricultural models that I presented here, basically these numbers of degrees of freedom are easily violated. So for example, a simple evapotranspiration model requires climatic variables like temperature, solar radiation, humidity, and wind speed, and soil properties like soil moisture and soil textures has to be known. Vegetation characteristics like the plant type, leaf area index, and crop coefficients, and also management practices are important, like irrigation and mulching. So, and these things are also like human-induced, so they give them even this whole system another degree of flexibility. And yeah, another topic that comes into play as well is that in environmental system modeling, often you have to do deal with chaotic processes. What is shown here on the right by that figure that shows the Lorentz attractor that gives the famous butterfly effect its name, and in chaotic systems it might might happen that if you start at the very stable situations, you run into an area that is well defined for the solution, but if you are running in a, let's say, start at a different situation, you might end up anywhere. So that makes it really tough, basically, to find good analog states, basically, for future predictions, and yeah, by looking basically into past data. Yeah, so with that, I would like to come to the last slide. While doing investigations for that presentation, I found a publication by Rosa et al. Who investigated yeah, the possibilities of irrigation in a 3-degree warmer world. And their results were actually quite promising. So they were stating that with deficit irrigation, with only rain-fed and monthly water storage, you can feed an additional 300 million people compared to what is possible now. And with something that what they called basically a hardware irrigation with a larger annual water storage, you can feed even an additional 1.4 billion people. And as we do have a lot of products that go into, let's say, will go into the irrigation market, I would like to answer the first question that I posed at the beginning, whether I think if we help to mitigate climate change, especially in the agricultural era, with a clear yes, I think so. However, the second question, I have to admit that whether we really help people most affected by climate change-induced droughts, I have to say that I'm actually not so sure if these really heavily technicized solutions are the best approaches to deal so. And that's also a topic I would like to discuss in one of the upcoming workshops. And yeah, with that, I would like to end my presentation. So these are my references I showed. And I would like to thank you for your attention.